Hello, and welcome to Answer Everywhere. Today we are taking a look at Ardupilot, which is a autopilot for drones and stuff. This is a JPL project. We just looked at PX4, which is another BSD project for autopilots. So I'm trying something new, which is trying to only do about half an hour. Time boxes at about half an hour, which means that we won't get to a lot. We'll barely get to anything, I guess, for the code. But I am trying to sprint through the end of the request that I've been working through, and that will help clear the way for the new blood. Hello, QSM. It's good to see you again. Okay, so what are we going to do? So if we only have about half an hour, and this is approximate, I'm not going to hold, I'm not going to be 100% on that. Let me set a timer. And let's do it. So we have a bunch of different things. Antenna tracker. I don't know what the antenna tracker is. Ardupilot, I'm going to guess, is for things like quadcopters and helicopters. Planes, I'm guessing those are planes. Probably submarines and not Subway sandwiches. Blimp is probably what PX4 was calling an airship. A blimp, a rover. I don't know, like a Mars rover, like a land vehicle. Or maybe a robot dog. Yeah, a rover is a glorified RC car. And I guess the thing that makes it Ardupilot is that it's built on an Arduino. I have my thermos full of coffee here because I woke up at 4 a.m. All right. Wait. Why is there precision landing for rover? So this is not a sensible place to start, but I kind of want to know what's going on. So we have init pre-canned. Pre and land makes sense. I don't know what C is for. And update pre-canned. And if you call update pre-canned, it just calls pre-canned update with 0 and false. And we init with 400. So I'm not sure why you... is this for like if you like land off, if you like roll off a cliff, or if you're doing like, if you're like running around a skate park? This is different. This is some landing page for telemetry. Introduction to rover. Getting started with rover. Selecting a frame. This is cool. It kind of tells you how to build one. Do any of the video demos show us landing? And a tractor. All right, one of these is a private video. Okay, so we have fences. Is fences geofences? Ardupilot plans to support a home-based cylindrical tin can and polygonal and or cylindrical inclusion and or exclusion regions. They are defined in Mission Planner under the plan screen. Okay, so I'm pretty sure this is the same as geofencing. I don't know what other way that you could implement fencing. All right. Okay, so I guess I may never figure out what the landing is about. Antenna tracker. A stationary installation on the ground or can be mobile, mounted on a vehicle, and moving at the same time as the vehicle it is tracking, such as on a pursuit vehicle. Okay. Theory of operation. Antenna tracker receives real-time GPS reports from the vehicle being tracked in the form of global position int messages sent by Mavlink radio, or possibly a hardwired serial connection. A hardwired serial connection between two moving vehicles? So antenna tracker also knows its own current position, and based on these two sets of coordinates, it calculates the magnetic bearing and elevation to the vehicle. I guess magnetic bearing is like compass bearing. It then moves the tracker servos until the antenna and the antenna tracker processor are aligned with the desired bearing and elevation. At this stage, the antenna is pointed straight at the tracked vehicle. As the vehicle and possibly the antenna mount itself move around, the servos are continually moved to track the vehicle. It only supports closed-loop feedback to position the antenna. Okay, so initially I thought this was going to be for like maybe tracking enemy vehicles, but enemy vehicles aren't going to open up a radio connection with you and transmit their GPS signals. So this must be for something else. We have Mav proxy. I don't know what Mavlink is. So let's find out. Mavlink. It's a header-only message marshalling library. Okay. It's a protocol. I don't know what the underlying like carrying layer is. But it's for exactly this, transmitting information about unmanned vehicles. All right, cool. All right, so rover is mildly interesting, but I feel like planes and copters are maybe more where it's at, although subs are also cool. And again, I'm going to assume that it's mostly PID control. Modules seems to mostly be Git submodules of other projects. So we'll go ahead and ignore that. So here's Ardupilot. I think we looked at some, let's look at planes. Here's attitude.cpp. And I guess we'll look at the arduplane.cpp. Log is probably just logging. And then we have plane as opposed to arduplane. And RC channel, presumably remote control. VTOL assist. Oh, VTOL is vertical takeoff and landing, right? So I had said in the PX4 repo that VTOL might be volatile, but now that I'm seeing it in both repos, I'm pretty sure it's vertical takeoff and landing. VTOL. Vertical takeoff and landing aircraft is one that can take off and land vertically without relying on runway. Yeah. All right. Avoidance is probably maybe not crashing. You have this a whole file for whether we are flying is flying, and then different modes like mode auto. I'm going to guess autopilot, mode cruise. This might be just like cruise control, maintain constant velocity. Mode loiter. I don't know. Loitering is maybe it's like flying around in a circle, but there's different modes. You might be a quad plane. Soaring. Servos. Tilt rotor. All of this is potentially cool. We'll just peek at a bunch of it. Tuning, I'm going to guess this is actually maybe closer to the... this is presumably tuning the parameters of the control model. What was I going to look up? Loitering or... Oh, I was curious about quad plane. How is it different from a quadcopter? So it looks like a quad plane has fixed wings and 4 whirly motors. I don't know if the motors ever point up. All right. So let's plow through these. Let's go first to tuning dot the tuning header. If AP tuning enabled. All right, so we have some tuning set. I don't know what a tuning set is, but we have a list of them. A table of tuning sets. I'm going to guess a tuning set is just a, each, for each thing that we're controlling, we have a collection of parameters, such as the P, the I, and the D terms, assuming this is PID control. And this is maybe just triples of those, or maybe there's other auxiliary stuff we need in there. We have a tuning func, which can be one of several types. It's an enum. Tuning rate roll pi. I guess pi as in the proportional and integral terms, and probably not the constant pi. But we can also roll P, roll I, and roll D separately. Roll. Okay. I see. Tuning rate for roll, as in, I guess, the roll of the aircraft. And I don't know why PI is its own separate thing, but it is for all of these. And then we have another tuning rate for pitch, and then for yaw. Yaw. Roll, I feel like, is the angular momentum around the axis, but I'm not actually sure this is true. Yeah, okay, that is true. So roll is like if the airplane is a hot dog, it's like spinning in its little skewer. Pitch is if you put a skewer right through the people who got the wing seats with the bigger seat, the foot length area, and you spin it around that way. And yaw is if you pierce up and down through the thing and spin it that way. All right, and so you can tune those with the PID control. Tuning angle. I guess this estimates the angle for those things. And then we have tuning PXY. Again, the non-vertical directions seem to be being estimated or at least tuned separately from the up and down control. And then V and A are presumably velocity and acceleration. So it seems like we're trying to tune position, velocity, and acceleration separately. I guess that makes sense. Although it's not immediately obvious. It seems like in theory you could tune one and then the others would change with it. So I'll ask Gemini. Let's try voice transcription again. I'm creating a library for a PID control of aircraft. Period. Should I control the position, velocity, and acceleration separately? Question mark. Or should I only control position and leave velocity and acceleration as determined by the change in position? Well, it was punctuated like a madman, so I can maybe make its life easier. So Gemini says they recommend only controlling position because PID excels at position control. Velocity and acceleration are derivatives. Aircraft dynamics are complex. Factors like wind gusts and varying flight conditions can significantly affect velocity and acceleration. Directly controlling them can lead to overshoot or instability. However, there are nuances to consider. For specific maneuvers requiring precise velocity control, for example landing, you might explore cascaded PID loops, where the outer loop controls position and the inner loop controls velocity based on the outer loop's output. And then gain tuning. All right, well, Let's ask ChatGPT. We're now getting into the sort of questions where these AIs, by giving a wrong answer, could kill a bunch of people if they're controlling aircraft or influencing the design of aircraft. It is crucial to understand the relationship between position, velocity, and acceleration. Here are the considerations: simplicity, reduced complexity, and natural integration. These are like, I've noticed that the responses are very similar very often. Recommended approach. For an aircraft PID control, a common and effective approach is to use nested or cascaded control loop structure. With an inner loop, directly controls the angular rates, velocity, and sometimes acceleration. This loop ensures fast and precise stabilization. Outer loop, or attitude or position control, controls the position or attitude of the aircraft using outputs from the inner loops. This is the opposite, right, of what Gemini is saying. Gemini is saying maybe control the position. Where's the cascading thing? Where the outer loop controls position and inner controls velocity. And here, oh, this is the same, they're just in the reverse order. Okay. And I'll ask, how does Ardupilot do it? Here's a breakdown of how Ardupilot typically handles these controls, particularly for aircraft. So the inner loop, rate control, attitude rate control, this is the innermost loop and controls the angular rates, pitch, rate, roller rate, and yaw rate for the aircraft. And then separate PID controllers are used for each angular rate. These controllers receive commands from the outer loop and adjust the motor outputs to achieve the desired angular rates and fast response. This loop operates at a higher frequency, providing rapid response to stabilize the aircraft quickly. Okay, so this is a really good point. If you want to stabilize the aircraft, so even if you can't move forward or backward or up or down, you should at least not be like spinning wildly. So these are obviously drones for toys. You don't have people inside of them. But I think the same principles overall apply to other aircraft. And it makes a whole lot of sense that the first priority is that like your aircraft is not like doing barrel rolls as it's flying forward. And so it really makes a lot of sense that that's the inner loop and that you have a PID controller separately for all of those. In the outer loop, attitude control generates a set point for the rate controllers in the inner loop and separate PID controllers for roll, blah, blah, blah. And this is an intermediate response. This operates at a slightly lower frequency than the rate control loop and focuses on maintaining or changing the aircraft's orientation. Okay, so the inner loop is stabilizing, making sure that you're not spinning crazily, but like sometimes you do need to turn or like, go like this for some reason, bank to one side. And that is done by this attitude control, I guess. And that's setting the set point. And then once that set point is set, the faster loop, which is going at a faster rate, is going to, as you're banking or whatever you're doing, the inner loop is going to make sure that you are stably banking as opposed to like oscillating crazily while you're banking. And then we have an outer loop position control. This loop manages the position and velocity of the aircraft, generates set points for attitude controllers in the outer loop. Okay. And then there's some stuff about quadcopters. I'll say draw an artistic rendering of cascading control loops. And while it's drawing, let's go back to the code. So we have this more tuning set stuff. And so the tuning sets are named after the things that we're controlling, which lends credence to the theory that they are basically just buckets of parameters from the controllers. So that's the header. Does the tuning.cpp file have the actual tuning? We can set, these are like setters and getters. No, it doesn't seem to actually have the tuning. All right, we have servos.cpp. This should be the, is there a difference between a servo and a motor? An AI servo, a servo mechanism, a device used to provide control of a desired operation through the use of feedback. Here's an example of a small RC servo mechanism. It has a 1 electric motor, 2 position feedback. Okay, so wait, no. What, here, position feedback. I don't, this looks like 2 leads that go into this plastic thing. But at any rate, we have the motor, and we know where the motor is because we have some measurement device on it. Oh, sorry, position feedback potentiometer. Okay, so this is some potentiometer, and this plastic thing is, I guess, just some gears over its little stick-outy thing. I don't know what any of this stuff is called because I don't know anything about electrical engineering, but I play guitar, and so sometimes you have to. These are the guitar knob things, and that's what they look like. So I think this is just some plastic device over this, and then some gears attached to it. And then 3 is the reduction gear. Okay, so we're reducing the gear ratio, I guess. And then 4 is an actuator arm, which is maybe the thing that does work. So this is linking me to a hard drive thing. An actuator is a permanent magnet and moving coil motor that swings the heads to the desired positions. All right. So that's a servo mechanism. It's not just the motor, but it's also the ability to measure where the motor is. And I'm not really sure what the actuator arm is about. But if we're learning about this stuff, we might as well figure it out. So here's, I don't know if this is any more informative. We have some, 1 is the base. That's some breadboard. 2 is the arm link. I guess the link to the robot arm. The servo motor is just this one thing. That's not what I want. How about components? Okay, so we have gears again, we have a motor again, a control circuit, position feedback sensor, and a rotating shaft. So I guess the rotating shaft is the thing that's driven ultimately by the motor. The motor's making turnies, and the turning is rotating the gears. And as stuff rotates, I guess this shaft maybe rotates. Maybe that's a potentiometer again, or something. But somehow it's giving a read off of what the position is, and the control circuit is somehow doing stuff. It's sending information about its position, presumably. Otherwise, why would you report it? And you definitely need it for the control. And then somehow you send information about how to perturb the servo so that it goes, it changes its behavior in the way that you want it to. In the interest of beating a dead horse, I'm kind of interested what this more detailed diagram is up to. We have a ball bearing. A winding. Current flows in the winding to create a rotating magnetic field. That's how a motor works. A stator. In the position of the rotor, a rotating magnetic field is created to efficiently generate torque. You have the shaft. This transmits the motor output. That's okay. The shaft is probably the thing that I was trying to think of the name of for the potentiometer. A rotor, a high function rare earth or other permanent magnet is positioned externally to the shaft. Okay. And the encoder, the optical encoder always watches the number of rotations and the position of the shaft. Okay, so in this example, where the way that we're reading how fast things are rotating is that we have some optical encoder, presumably maybe something like a laser or a light that is able to detect how often it blinks, and somehow as it's rotating, it blinks maybe once per rotation. And then we get that information from the encoder cable, and then the motor cable does what? I don't know. Maybe it controls the motor. Okay, so that was a detour into servos, but now we're going to look at servos.cpp. And we have things like we're in Ardupilot. So we have plane throttle slew limit, which takes in a serve channel, aux servo function T func. And if we have quad plane, then we might do some stuff. If we're not supposed to do throttle slew, then we set slew rate, I guess, to passing the function, setting something to 0, setting something to 100. I guess maybe these are like the default values since we're not supposed to be throttling whatever GDT is. Otherwise, we get the slew rate by calling aparm throttle slew rate. I don't know if I saw where aparm was, etc. Here's similarly suppress throttle. We want to suppress the throttle. We think we are on the ground and in an autopilot controlled throttle mode. Parachute enabled. Huh. I guess maybe occasionally you have a parachute. All right, so this doesn't seem to be really down in the servos themselves, but SRV channels, I'm going to guess, is like the thing that actually talks to servos, and SRV channels set output scaled. And we're passing in K flapper on left and flapper on left. So maybe we can look at the serve stuff. Serve channel. This is some external library, I think. Or maybe not. All right. Control of servo output ranges, trim, and servo reversal. This can optionally be used to provide separation of input and output channel ranges so that RC, N, min, max, trim, and rev only apply to the input of the RC channel. It works by running servo output calculations as normal, then remapping the output according to the servo min, max, trim, rev from this object. Okay. So this is maybe some configuration for the different servos. Some stuff about GPIO pins, flap automated, aileron, roll, open. I guess these are all like different servos on the plane. Motor 1 through 8. I guess you can have up to 8 motors. And so on. All right. We have only 2 minutes left. Let's see if there's anything super fascinating here. So Ardu soar support function, update soaring. Check if soaring is active. I don't really know what soaring is. Thermaling. We are currently thermaling. Suppress throttle and update the thermal mode. Is thermaling like sailing along a like an isothermal? Introduction to thermaling. Thermals, part 3. My favorite part of flying is undoubtedly thermaling. In fact, thermaling may be my favorite thing to do in life. I think it's like riding waves of the air. I'll see. Tell me about thermaling in aircraft. Used by pilots of gliders or sailplanes to exploit rising currents of warm air to stay aloft. The source of lift. Sunlight heats the ground, which in turn warms the air in contact with it. This warm air is less dense than the cooler air surrounding it. They look for visual cues like buzzards circling or fluffy cumulus clouds, which often form over thermals. Okay. There's the opposite of an isothermal. It's like a place. It seems like a place where mm, uh, vertical movement of the due to thermal differences is maximal or locally maximal. All right, here's mode loiter. Do loiter at location. Set up terrain target alt, plane next, WP lock. We have a loiter center lock location. Calculate relative position to the vehicle relative to loiter center, projected onto the closest point of something. Their lines are too long. I refuse to scroll. Corrected radius for altitude. So I think that we really are just like circling. But I'll look up what loiter. We have a radius and we have a center. So how could we not be circling? Loiter is the phase of flight consisting of flying over some small region. Generally at the end of the flight. Okay. The prefix circ does not occur in that article. What's it called when an airplane has to circle? It's called annoying. It's called a holding pattern. Back when I was writing software for UAVs, we called this loitering. Loitering is traveling, usually orbiting, at the best endurance speed to maximize how long you can stay there for. It's not specific to waiting to land, and you might not even be loitering. In the situation described by the question, you might be burning fuel to reduce landing weight. Okay, so it seems like I don't know if loitering must involve circling, but it seems like there's some ways of circling that don't count as loitering because you're not trying to minimize fuel usage. Avoidance, ADSB. I'm guessing this is about not crashing. Handle recovery, check flight mode. Handle avoidance critical. There's some obstacle, okay. And there's horizontal avoidance. And now I'm curious about handle recovery. Handle recovery. Check we are coming out of failsafe. If plane failsafe ADSB, then we set ADSB to false. Whatever GCS is, looks like some messaging system. We're going to send a text message MAV severity info. Avoid resuming with action with some recovery action. I guess when you handle recovery, you send it a recovery action. If the control mode reason is avoidance, restore flight mode if requested and user has not changed mode since, then we switch depending on the recovery action. We might remain in avoid ADSB, in which case we'll do nothing. We'll stay in the avoid ADSB mode, which is guided, which will loiter. Is ADSB is this like an aircraft protocol? I feel like I've seen that acronym, but I don't remember anything about it. We can resume previous flight mode, whatever RTL is, and so on and so forth. Okay. VTOL assist, we don't need to see. Plane, maybe we'll just quickly look at what makes it different from an Arduplane. It's got a pretty long amount of code. We have parameters like G and G2. I don't know if that's gravity or something else. Some stuff like are we in calibration? GCS. I don't know what GCS is. UAV ground control system. So I guess it's sending a message to ground control. And then what is ADSB? Yeah. Automatic dependent surveillance broadcast. Provides real-time something or other. Okay. So ADSB is some way of, I guess, broadcasting where planes are, I think. And this GCS thing that we saw was sending a message. It seems to be just sending message back to the control or ground control, which is like the human with a laptop or a phone or whatever that's making the robot plane do its thing. We have a bunch of modes like mode circle. I guess mode circle is different from mode loiter. Fibwub, mode cruise, auto tune, which I'm going to guess is different than like T-Pain style auto tune. All right. We're out of, my timer has gone off. So I'm going to stop, although I'll look quickly at the files we've opened. So Arduplane, we're including plane.h. So we're kind of just like decorating the base plane with maybe Ardupilot related stuff. And update speed height. Out of the corner of my eye, I read this as update speed light, which is something you can't do. Plane 1 second loop. Make it possible to change control channel ordering at runtime. All right. And then there's some scheduler stuff. This is attitude, which I'm going to ignore. Sub. I'm also going to not look at because we're out of time. But I'm curious if we can find anything more about cascading control loops or maybe nested. I'm guessing that this won't be in any obvious place in the code. We do have a scheduler. I don't know what HAL Sittle is. AP is probably Ardupilot. HAL is, who knows? I'll look up Sittle. Simulator? HAL simulator? We have parameters. We have tuning. Isn't that what we looked at? There's reload value, set value, save value. Roll controller, KP. We have this APM roll controller thing. You can do things. So in this APM control library, you have things like pitch controller, roll controller, yaw controller. I guess let's look at pause controller, position controller. We have things like is active, set limits, set turn parameters, get speed, max speed, max jerk. In it, this should be called before. There's some initialization function. Adjust position, velocity, etc. by setting a target. You get desired speed. Get outputs for forward back speed in milliseconds, lateral speed, and turn rate. And they're just going to return the desired speed. But I'm kind of curious where the logic is to actually compute to actually do the tuning. So let's maybe look in the implementation file. We have this var info thing. And update. I'm guessing update is what we want. So it's going to take float and it describes it as DT, which is maybe change in time. Exit immediately if no current location, destination, or disarmed. Okay, so we might exit early. Check for EKF XY position reset. I don't know what that is, but that's maybe some kind of error or side condition, like a corner case. If no recent calls, reset velocity controller. Okay, if we're not active, I'm not sure why. And then we calculate the position error and convert to desired velocity. So we set velocity target to 0. I guess is probably what that does. And then if the position target is valid, then we get a vector 2p position target, 2p, presumably a vector of length 2, p maybe because it's position. But we get the position target, but it's just set to the position target. We're making a copy of it, I guess. And then we set the velocity target to whatever p pos is. P pos update all, position target x, position target y, and then current position NE. So this is presumably the vertical position. I don't know what NE is, but it's basically not being updated, right? Because we're just doing, I think, X and Y separately. Calculation of velocity error. We'll say that we are not stopping. And if the velocity desired is valid, then we'll add the target velocity to desired velocity from position error. So, wait. How do we actually compute the error? So the maybe this update all is doing position error somehow. We'll have to look at this update all thing. But at any rate, this is the desired. This is what we think is the target velocity, I guess, and we're just adding it to. Oh, we're adding the desired velocity to the target velocity. Why adding as opposed to subtracting to get the error? I don't know. And then we set stopping to whether the desired velocity is 0. And then we limit the velocity to the maximum speed. Velocity target limit length. So length in the sense of the speed is given by the norm of the velocity vector. And so we're just renormalizing the vector so that it stays within some ball of some radius. And then we limit the velocity to present fence violations. We say that backing up is false. And if AP avoidance is enabled, then we do some calculations about fences, I guess. And I suppose as we're approaching the fence, we need to somehow steer in a direction away from the fence so that we don't pierce the line that we're not supposed to go through. Then we calculate the limit vector based on steering limits. Okay. There's some steering limits. I don't know what those are for, but this is again just some restriction on the velocity. Then we calculate the desired acceleration by calling PID velocity. So what did we call up here? P pos. Okay, so P pos I think means that the position controller only uses the proportional term, and then the velocity controller uses the P, I, and D terms, and we're going to call update all with the velocity target, the current velocity ned xy, dt, and steering limit vec. So, this, I'm guessing, I'm not sure. We'll look at this function. But this I think takes more arguments because it has more terms in its controller. I'm guessing this is the p term. I don't know which of these are the I or the D term, or maybe they are computed by the function. Then we check if the thing we just, or rather we check if the acceleration desired is valid, in which case it is. We add the target to the desired acceleration. And then we do some other kind of like clamping and reduction stuff, it looks like. The I term is zeroed in forward back direction. Convert desired acceleration to desired forward, back speed, etc. Okay, so it looks like these update functions are the things that actually do the, maybe do the calculations. And so this, I guess, is probably where it's defined. Update all, AC PID update all. Set target and measured inputs to PID controller and calculate the outputs. Target and error are filtered. The derivative is then calculated and filtered. The integral is then updated based on the setting of the limit flag. Okay, so the first argument is target. The second argument is measurement. So this is the goal. This is where we are. dt is what? The change in the time. Then we have some limit and something about boost, which I'm not sure. We don't allow infinite targets or infinite measurements. And if you try to send it an infinite target or measurement, you get 0 back. Then we reset the input filter to the value received. I don't really know what it means by input filter. And the target is target, error is target minus measurement. Derivative is 0, target, derivative is 0. And if AP filter is enabled, then we do some other setting stuff. Otherwise, we say error last is error, target last is target, and error is the difference between them. And I'm going to ignore the filter and it, oops, no, don't do that. I'm going to ignore the filter stuff because I don't know, what it's about. Okay, so if we're not doing the filter stuff, then we call it get filt t alpha of dt times target minus underscore target. So something about, I don't know what t and e are. So I guess target and error. And I don't know what alpha means. But something, this is like a, I guess we're maybe beginning to compute the derivative. We have this difference vector, and we're multiplying it by dt and something about filtering. And calculate and filter derivative. So if the dt is positive, which I hope it is, the derivative is the difference between the error and the previous error divided by the time step. And then we're going to add to the derivative the get filt d alpha of dt times derivative minus derivative. Or derivative minus underscore derivative. I don't know what the filtering stuff is, but we should take a look at it. And then the last thing I guess we do is we check if the derivative is positive. We check if dt is positive, the time step. And if it is, then we calculate, I think I looked at this, the float derivative is the difference between error and error last, the current error and the previous error. So the progress we've made in the error divided by dt. And then that, then through some filtering operation, we get this get filt d alpha thing. And that, again, I'm not sure what that does. And then we set target derivative to be essentially the same thing as the error derivative, except with target instead of error. And then we update the I term by calling update I. And then whatever P and D out are, I guess position output and derivative output, not position, proportional. The P and D terms of the PID controller, we have some weight KP for the error and some weight KD for the error. I don't know where those are computed or tuned, but there might be a slew modifier for P plus D, and I don't know what that is. The maximum rate of change of an op-amp's output voltage. In mechanics, the slew rate is defined as the change of voltage or current or other electrical or electromagnetic quantity per unit of time. So this is something that's defined for digital thingamajiggies. I don't know if this is like some property of the servos or if something else is going on. We can look it up. To help reduce or eliminate oscillations in control loops due to excessive tuning gains. So I guess the theory of the control theory came from electrical systems originally, and so I think that they maybe just used some of the same terminology. All right, so I think that's what this is part of. And then we have this DMOD stuff. DMOD, I don't know. The there's a PID info.dmod. We're multiplying the P out and D out terms by that. And then we might boost them by multiplying by some boost, essentially scaling them. Then we set the PD limit to false, and then we might apply some PD limit, whatever the PD is. Then we return P out plus D out plus integrator. So the sum of the terms the terms already include the factors, the scaling factors, or the constants of proportionality. And what does that leave? That leaves us what's going on with the alpha, filter T alpha. Get the target filter alpha. Calc low pass alpha DT. Okay, so this seems to be some low pass filter. What is alpha? I don't know. And why do that? Target filter. And then let's see if we can find this function. Calculate a low pass filter alpha value. So we give it a DT and a cutoff frequency. So I guess the idea is that if it's low pass, so it cuts off things that are too high, so things that are fluctuating too rapidly. So we check if it's negative. If either the DT or the cutoff frequency is negative, then that's bad. So down here we assume that I guess both are positive. If the cutoff frequency is 0, then it's cutting off everything, I guess, and then we return 1. If DT is 0, then we return 0. Otherwise, we calculate RC to be 1 divided by M2 pi. I'm going to guess it's just 2 pi, and maybe M just means math. So this is just 1 over 2 pi times the cutoff frequency. And we return dt divided by dt plus RC. And y. So if the cutoff frequency is low, so close to 0, let's say, then this fraction is close to infinity. And so the thing we're returning is something smallish over infinity, so it's close to 0. And I guess as the cutoff frequency gets larger, this RC thing becomes itself closer to 0, and we're returning closer to 1. So this is a fraction, I guess, between 0 and 1 that scales. I guess you're going to maybe multiply the result of this by the dt to scale it down if it's too fluctuating. Is that what we do? Let's go back to update all. Yeah, okay, so we're passing. Well, hang on. Get felt d. So I don't know what the frequency is not here. I guess it's implied somewhere. We're not multiplying it by the dt. We're multiplying it by the difference between the derivative and underscore derivative. And what is underscore derivative? That's the input filter. So let's find out about Ardupilot input filters. I think we're way over half an hour. But now we're not really learning about Ardupilot so much as we're learning about control. So we have a bunch of filters here. Some of are Kalman filters. I don't think these are Kalman filters. RC input and output. No, I don't think that's what this is. Input filter. Let me ask the AIs. In Ardupilot, PID implementation, what are input filters? Input filters are used to pre-process the input signals to the PID controllers. These filters help improve the stability and performance of the control system by removing noise and unwanted frequencies from the sensor data before it is used in the PID calculations. Okay, so I guess the way that we're supposed to think about this is that it's cleaning up the sensor data, which can be noisy. So low-pass filters, the purpose is to remove high-frequency noise from the sensor inputs. That makes sense. A low-pass filter allows low-frequency signals to pass through while attenuating high-frequency signals. This is particularly useful in applications where sensor data, for example, accelerometers and gyroscopes, may be noisy. Typically, a simple moving average or a more complex filter like a Butterworth filter can be used. Notch filters attenuate specific frequencies that are known to cause problems, such as resonance frequencies of the aircraft. Okay, so if the aircraft has a specific resonance frequency, then it makes sense that it might oscillate at that frequency, and that would cause, I guess, the sensors to detect that oscillation, and we want to remove those through notches. Essentially, the frequencies to the left or the right aren't really problems. It's just that one resonance frequency. So high-pass filters, these are just the opposite of low-pass filters, to remove low-frequency components that might represent drift or bias in the sensor data. Drift or bias. Okay, so a high-pass filter allows high-frequency signals to pass through, less commonly used in PID controllers. Okay, so these are these are different filters, and the way that they're implemented is the way that we see. I'm not going to go any more into these filters. But that's something that I didn't really know about. All right, and I guess that's really all I wanted to see with the autopilots. We saw how things are controlled. We saw a little bit about PID control and control theory as applied to flying machines of various kinds, as well as submersible boats, which we didn't really look at, but it's there. It uses a lot of the same framework, and similarly for rovers. And both PX4 and Ardupilot look pretty complete. Maybe just because it was the second one that I looked at, but it seemed like the Ardupilot code was a little bit easier to look at and get a grasp of. And it seems like maybe they have they've implemented a wider variety of features, perhaps. Although that's not always a good thing. I don't know enough about this space to say anything about whether one or the other is more appealing for any particular application. But it's a really cool space. I hadn't really considered it until a viewer recommended looking at these repos. But now I kind of want to build some sort of device, either a plane or a boat. But we'll see if I end up doing that. If so, I'll show you guys what's up. All right, that's all for today. Thanks for watching.